We were looking at the MOS transistors, how they are being used as switches. So if you want to have a switch application, right, basically it is used to control the flow of current, right, in any circuit. So here, in case of a MOS transistor, we know that the gate is the terminal which acts like a controller, right, and by changing the required gate voltage, right, we can definitely control the amount of right current flowing in the device. So our intention is to see how this technique or how this can be achieved in NMOS and in PMOS. So first we started with the NMOS, right, and in NMOS, uh, right, let us assume that there is no gate voltage applied, right, so which indicates there is no channel, right, so no connection is between the drain and source terminal of the MOSFET, and we say that the switch is off. So symbol for switch off device is as shown here. Then let us assume that now we have applied the voltage to the gate terminal, and slowly we are increasing. As you increase the voltage, we know that below the gate, in the junction of the body, that is silicon, p-type silicon, and the SiO2 layer, you have electrons coming and accumulating, right, and at a particular voltage there will be sufficiently large number of electrons so that you can consider that there is a channel between the drain and source. And when that happens, right, if you apply the voltage to a drain, and if you connect the body of the MOSFET and the source to ground, right, it is clear that there will be a flow of current. So drain has to be connected to positive voltage, okay, right, only when in that case there will be flow of electrons. Applied voltage, source will be grounded, okay. So if that is the mode of connection, right, we can say that yes, transistor is on. So this is the case of N MOSFET only. So how the N MOSFET can be made to work in this fashion? Yes, this is the answer. All right. Okay, now we move on to the PMOS. Okay, so in the PMOS transistor, yes, when in case of a NMOS, when there is no gate voltage, device is off, switch is off, right? When it's, yes, yeah, yeah, we have slightly modified. This is actually inverted version. So whatever we studied in the NMOS, it gets inverted when it comes to the PMOS because the polarity is reversed, right? So NMOS in the sense N channel, now PMOS indicates P channel. So P channel should have more holes compared to the electrons in the previous case. So here voltage is not negative. You apply no voltage or full voltage, once again 0 or 1, right? But in order to turn off the device, you apply high voltage. Okay. Gate is at high voltage means device is off. Gate is at low voltage or no voltage means device is on. Right? Okay. Yes, so PMOS is in that case. All right. So here let's quickly recall what is the structure of a PMOS and how will be the connections. All right. Anyway, let me draw something very quickly so that we don't miss out the uh, polarities. Okay. So let's say we have the two. One is for drain, one is for the source, okay, and let us say we have the, this is the SiO2, and above that we have the polysilicon. Okay, now let me make the connections, right. So let's say this is as known. We know that this is the source terminal. This is the drain terminal. Okay, and this is the gate. Okay. Now the normal way of making this device to work is, okay, let me write the uh, various regions now. So if you want to have the N channel, the substrate was P. Now I want P channel, so this is N. Okay, N, this is substrate. It's the body of the transistor. Okay, then I need, this is P plus. Previously we had N plus for N MOSFET, right? Now P MOSFET, so this is P plus P plus. Okay, so as usual, this is source, this is drain. Now we need to reverse the polarity, in the sense, you see, the drain will be connected to, right, drain is connected to the lower voltage. So previously drain was high voltage, now the drain is connected to ground. Okay, then, right, in order to make this to conduct, right, you need to connect the source, right, and the body of the MOSFET, right, both of them will be connected to what is called as a positive of your battery. This is plus positive voltage. Okay, and this is connected to ground. Now you see, this is how it's the connections are made. You can see this is a positive terminal now. So yeah, I'll come to the gate. Okay, right, so this is plus high voltage to the source and the body of the MOSFET, they are at high voltage. Okay. So if you apply a voltage V here, that V is applicable to the source as well as the body. Previously, both were shorted, yes, and the source and the body of the MOSFET were shorted, but they were connected to ground. Okay. Okay. All right. So you see that that is connected to ground. Now you see there is a change of polarity, right? In this sense. Now, let us say in the normal condition, and let me say that I need to do the reverse. So what happens? Let's say that this is initially connected to a positive voltage. You need to start with the analysis in that way. So okay, anyway, I'll first let me write it in this fashion. So let's say that this voltage is positive, the gate voltage is positive, correct? Now I know that, right, the body of this MOSFET is connected to a higher voltage, correct? So that means this positive voltage actually has there are a lot of electrons in this region, right? This whole region has a lot of electrons, right? So it means I have electrons everywhere. So you can see bottom side of the whole body is connected to positive voltage, as well as, right. So because since this is positive, I have electrons here everywhere. I don't see P existing between the drain and the source. Are you okay? So this means, right, when the gate voltage is positive, the device is off. Basically, there is no connection between the drain and the source. Now I keep reducing this voltage, right? As you reduce this voltage, what happens on the other side? I have a bigger positive voltage, right? Because this voltage is bigger now, because gate voltage is reducing means there is a higher voltage on the other side of the device. Hmm. So here you have actually electrons only now, completely filled, because it is N substrate. Inside the P there are no electrons. Okay, right. Now yes, yes, there are electrons only in this. So when we are trying to reduce the gate voltage by performing this operation, right? What exactly happens is, because of there is a bigger voltage on other side, right? Somewhere here, you see all the electrons will keep moving towards that voltage, correct? Because electrons are getting attracted by the positive voltage, bigger positive voltage on the other side of the device. When electrons move, it means you are creating holes over there, right? If there is electron, that is a free electron, which means it's negatively charged. But when electrons move out from a location, right, there is a positive charge now, correct? So as you keep reducing this voltage, it's not negative, it's I'm slowly reducing the voltage, that's all. Okay, electrons keep moving away and you find holes over here. When this when the gate voltage is reduced by a sufficiently large amount, you see the when this gate voltage keeps on reducing, we understand that there is accumulation of positive charges below the gate region and the oxide layer and the N substrate. Right? As I have shown here, you can see the accumulation of holes. Right? And when the voltage is sufficiently lower, right, I can find the source and the drain regions of the P MOSFET getting connected using a P channel, right? Because there are more sufficiently large number of positive the holes, right? So holes on P plus side of source as well as P plus side of the drain, now they are getting connected by the channel, right? So channel comes into picture only when there is a sufficiently lower gate voltage, not at a higher gate voltage. Okay, so now we'll explain the whole process, okay, in words. So we know that in case of a P MOSFET, right, the body of the transistor is at high potential, right? So we know that in a PMOS, I started already that sentence, the body is at high voltage, right? Source and drain junctions are reverse biased, correct? I just mentioned that word reverse bias because the N is at a high potential and P is at a lower potential, right? Normally forward bias means P junction should be higher voltage compared to the N, correct? Now it is reversed, correct? So therefore the D drain and S for source, right, junctions are reverse biased. Reverse bias. I'll just show you the reverse bias once again just to make things clear. All right. So you see the voltages here. This is a positive voltage. This is a positive voltage. This is a negative voltage. Right. Yeah. So this is very clear that N region positive, P region negative, negatively connected in the sense ground. Okay. That means it is reverse biased. Correct. There is a PM junction. It is reverse biased. Yeah. At the same time, you look at this, right? They are equal. Equal is also non-conducting, so you can call it as a reverse bias. Okay. Right? It's a reverse only. Conducting means forward. Non-conducting is reverse. Okay. Right. So you can. It's very clear that this sentence is valid. Right. So drain and source junctions of my device are reverse biased. What do you mean by reverse bias? This means there is no current, correct? No current flow, right? When there is no current flow, this means what? The transistor is off, right? Yeah. This means, right, the right now the gate voltage is high, right, and now we try to reduce this voltage. Okay, so when the gate voltage is reduced, let us try to reduce the voltage. What happens? The positive charges, or you can even write holes, okay, they get attracted, they get attracted towards which region? The interface between the N plus N region and the gate, the junction between N substrate and gate, correct? They get attracted to, yeah, right. So they get attracted to the, I can write substrate and gate junction, that is below the gate junction, correct? Below the gate region, right? Now again at this point they are just getting attracted right now, but at this moment there is no channel, correct? But when the gate voltage is sufficiently low, when the gate voltage is sufficiently low, what happens, right? This implies, right, a huge number of holes present, right, in the region, correct, forming a channel where between the drain and S. Are you okay? Yeah. So between this, it's existing now. So this means the transistor is on. All right. So let's write the notations quickly. So we know that this is how the PMOS transistor can be represented. So there is a drain, source, and the gate. And the gate, right? So the on condition is, once again, right, you will short the two terminals, right? So this is drain, this is source, this is on. And if you want to denote the off condition, oh sorry, not this, you will open the junction saying that there is my mistake, there is no connection between the drain and the source, right? So this is drain, this is source, and the open connection says that the voltage is actually high. Okay, so this is the overall idea of the application of a MOS transistor as a switch. So we have two options, PMOS and NMOS. PMOS works with lower gate voltage to turn on the device. At the same time, NMOSFET uses a high voltage at the gate terminal to turn on the device. Otherwise, both the devices are off. All right, moving on to the next topic. So we have uh, the types of MOSFETs we need to look now, that is in terms of the manufacturing process. Okay, so first we will look at the NMOS, right? NMOS, two types. Already we have, I named the two types. So now we are going to look at in detail. This is the enhancement mode. Enhancement mode, right, where you see that, right, the channel does not exist by default, right? So by default, in the sense, as you purchase the device from the vendor, you see that there is no channel. By just applying the voltages only, you can see the channels coming into picture. Okay, so if that is the specific way of representation of a device, then that type of MOSFET is called as N MOSFET. All right, okay, so now we define even some voltages here. So let's draw a diagram. Okay, all right, so this is the N type MOSFET. So I need to write a P type substrate, Right. Then now I will show you little bit of more details. Okay, so previously I just I was drawing only one small this thing here, but now I will draw two layers. Okay, this is, I have to show you even the depletion region. So depletion region refers to the junction, right? If a junction is forward biased, you have a smaller depletion layer. If the device is reverse bias, it has to be a thicker depletion region. Okay, if you remember the concepts of what you call diode, right? We actually have studied the thickness of a depletion region and how the depletion region changes, right? In terms of its width, also we have seen over there. Okay, so I'm writing that now. So this thick layer, what is outside right here, is the depletion layer. Okay, I'll come to that later. But before that, let's finish some of the this thing. So here you have, right, this is a gate. This is the oxide layer. Yes, I want to. Above that, yes, above that I have the polysilicon, right? Like this. And above this, I'm going to make the connection for gate. Okay, so I have the connections formed in this way. Okay, so let me write a line here. So this is connection for source, and this is the connection for drain, and let's say this is the connection for the gate. Okay, now anyway, it's a n-type MOSFET, so I am expecting this terminal, right, should be shorted, right? So that it should be connected to which one? It's the body of the MOSFET, correct? So we will connect in this fashion. So this is what is the connection to the body, right? And I know that these are the voltages, the notation for voltage. So this is source, this is gate, this is drain. Now this source is connected in this fashion and also it is grounded. So lower voltage is at this. So this is source, right? I can call this is Vs, but Vs is 0, correct? Grounded, right? Vg, there is a notation, standard notation in all the textbooks saying that this is called as Vgs. They are not calling it as simply Vg, right? It is called as VGS because source is already grounded. So even if you call simply VG or you call VGS, it is one and same. It is MOS transistor theory of the first chapter. Yeah, so this is the case, and drain voltage, whatever you apply, we denote it as VD. Okay, so you see that normally the polysilicon is this, right? This is SiO2, right? Here you have the depletion layer. So this is a depletion. This is also a depletion, right? So P substrate, this is N plus and this is N plus, right? Depletion in the sense it is a junction between N and P. Any N and P junction is a depletion. But you see, I have a width shown here, right? There is a width. This width depends upon whether it is forward biased or reverse biased. Now I am showing a thicker region here because both the junctions are reverse biased, right? In the sense, the same concept which we saw in the explanation of the P MOSFET. You see here, this is connected to negative. This is also negative. Correct? Negative, negative in the sense ground. So there is no conduction reverse biased. All right. So what is the connection for drain? Positive, right? Drain is positive, P is negative. N is positive, P is negative. Once again, here reverse biased. This junction is also reverse biased. That's why I'm showing the thicker region over there. Okay, so actually this depletion layer takes a lot of responsibility in the deciding whether to conduct or not. That's why we have to deal with the depletion layer when we discuss about this. Okay, so in this enhancement mode, right, this is the enhancement MOSFET. I don't see any channel there, correct? So you see that in this case of, in this kind of enhancement mode, right, normally we have the gate region, right, which is having an polysilicon. Below that I have a SiO2 that is deposited for insulation purpose. Gate should not be connected to the channel region, right. Now you see, when this gate voltage is zero, right, there is no channel, right. We know the we know the conduct how this conducts, right. Already we know that, so we don't write in detail now. Simply we'll go with the concept. Okay, so when VGS equals to 0, this means no channel, right. Why? Yes, we know there is positive charge, no electrons, right. But the next thing is that if VGS tend to be a positive, right, as you even increase the VGS slowly, correct, what happens? Electric field gets established under the gate region. Again, right, under gate, right, which results in what? There is a charge accumulating, right. So that means, see, there is a technical term. I'm directly bringing that now. So you see, inside a P substrate which has majority of holes or positive charges, because of this applied gate voltage, I have more and more negative voltage coming here. So means what? There is a change in the polarity of the region, correct. So that is called as charge inversion. I'll directly bring the word. So, okay, the charge inversion occurs, right? When the charge inversion occurs, it means it is a P substrate having N region, a small region of N over there, causing the conducting path or channel. Charge inversion occurs over there. This implies, right, the channel is formed. That's all. So channel is formed. Now you know how to make this to conduct. Apply a voltage to drain, and there is a current flow. Right. This kind of MOSFET is called as what? That is NMOS, enhancement MOSFET. Okay. Now let's go to the same N type, but it is a second mode of this thing. It is called as a depletion mode. So this is NMOS, depletion mode of MOSFET. Right. So the outer structure still remains same, except the fact that there is a inbuilt channel that exists. Okay, that's the only difference now. So what I can, okay, I'll just copy the same diagram and I'll make sure that there is a, yes, you will be having, right, a channel that is, yeah. Whenever you build what you call these, uh, the source and drain, you are building it inside the MOSFET, right? during that time itself you build the channel. Okay, only that's the option to do this. Okay, we have this now. So the change is this. We have the existence of the channel like this. So I have this connected in this fashion. Okay, I'll draw a straight line so that this looks neat. So I am connecting here to here, right? So, and I'm not going to have this part. See, I'm not going to have this part. It's connected, previously connected. So you already have this region like this. So you can see that, right? The N plus and N plus are already connected. So no need of building the channel, right? So you see that this VGS, right? If VGS is 0, still I don't have any problem, right? I still can conduct. Apply a VD, there is, right, conduction. But then if you increase the VGS, right, more and more electrons will come into place, correct? Now the channel width further increases, so you have more conductivity, right? So in this case also VGS will take care of, right, the controlling of this, but it has no control when VGS is 0. Previous case VGS 0 was completely turning off the device, correct? Now that is not happening over here. So let's write that one point here: enhancement and the depletion mode of MOSFET. Yes, correct. In depletion mode of MOSFETs, the source S and the drain D are connected by a conducting channel, right? But in order to control the, right, conducting channel, even when the gate voltage is 0. This is the important aspect. So previously VG was 0, no channel. The VG had to be a specific value to get a channel, but now it's not like that. So manufacturer will put a channel there built in, but the channel width can be controlled by applying a, right, voltage to the gate terminal, right, to control the channel width. The VG can be varied. Okay, so this variation of gate voltage allows the control of the current flow between the drain and source. Okay, so channel width can be varied to control the channel width. So hence controlling the current flow between drain and source. Okay, right. So, right, there is a equivalent idea behind the uh, P MOSFET, right? So how the P MOSFET is going to work in enhancement and depletion mode, I think this is pretty straightforward now. So let's write the diagram for PMOS. All right. So this is PMOS. First we'll look into enhancement mode, correct? So in the PMOS enhancement mode, we have this, then we also have two regions of this, and we have this. Okay, so this is source, gate, and the drain regions. All right. Now, as per our discussion, we know that there will be a positive voltage connected to the source, correct? So plus minus, this minus I connect to ground, but I am connecting the positive terminal to this. Okay. At the same time, this itself has to be, sorry, this itself needs to be connected to the body of the MOSFET, correct? Okay, let's it is grounded, it is grounded, correct? Ground is, you don't have to show the ground, that's okay. But when you are connecting to a positive voltage, it is always expected that you will show that voltage. Okay, so that's the reason why we are drawing the connection right now, showing that okay, it is connected to what do you call, it is connected to this region, right, the body. So this is the connection. Okay, now this is the required connection. I know that since it is a PMOS, this should be N substrate, correct? N substrate. So this is silicon dioxide, SiO2. This is the polysilicon. This is the P plus diffusion layer, and this is the depletion. This is also the depletion, right? I know that VG is when the VGS is connected to a positive voltage, right? So you don't have, right, the when this is positive, I don't have any channel, right? So VG, so here you see that the drain is actually connected to ground. So normally the value of voltage which we connect here is denoted in this fashion. So this is Vs. Now Vs has a value, Vs is not 0. Now Vd is 0. Okay, it is connected to ground. So this notation is VGD now. It's not VGS. PMOS is VGD because drain is at ground, not the source. Previous case VGS was written because source was connected and drain was not at ground, not at a ground potential. Okay, that's the only difference. So now in the PMOS enhancement mode, when VGD is positive voltage, a bigger voltage, there is no channel, right? And as this VG reduces or VGD reduces, more and more positive charges come and accumulate below the SiO2, right? That is going to form the channel between the, right, source and the drain. Are you okay? Yeah. Right. Now, next part is we are going to look at the depletion mode of P-type MOSFET. Are you okay? Yeah. Okay, let's go to that. This is P-type, or this is PMOS depletion type. Okay. So absolutely. because of this, there is a pre-existing channel now. So I can see that there is a channel which exists between this, right? So since the channel exists, even when VGD is high, right, there is a pre-existing channel, so that the conduction will not be stopped by making VGD high. But as the VGD reduces, right, there is more and more positive charge accumulation over here, right? Which means you can see that now the width of your channel is increased. I can further increase the channel like I did in the NMOS depletion by increasing the voltage over there. When you increase the voltage, width was increasing. Here you reduce the VGD to increase the width of the channel. That is the only difference between the PMOS depletion and NMOS depletion. But now what we see is that the current versus voltage characteristic of the MOSFET, okay, and N-type MOSFET. This is going to come now, right? So let's write the side heading like this. That is the current, that is ID, versus VDS, drain to source voltage, right? Plot of this is N MOSFET. Okay, so this is how it's going to look like. On the y-axis, I'm going to plot the current. So this current is ID or IDS because it is flowing between drain to source, right? So textbooks will call it as ID, the drain current, or drain to source current, doesn't matter. Similarly, you can measure the VDS, voltage between the drain to source. Okay, now by doing the experimentation, we can observe one thing, that there are two different regions, right, in any plot. So I'll differentiate the two regions, maybe say like this. I'll draw a line. This is not a part of my graph. So what I do, I'll try to erase some part of this graph. Okay. So this is just an ideal line saying that, okay, sorry. Yeah, we can plot ID versus VDS, but only one is sufficient just to understand the process, how the currents are going to flow. Okay, now, so the current is initially, it will be zero when VDS is zero. But as the current increase, as the voltage increases, it is going to increase in this fashion and it comes to a specific point like this. After that, after that point, you see that it will remain almost straight. It will remain a straight line. This is how the voltage plot, sorry, voltage versus current plot of a NMOS looks like. Now, we have the regions of operations of the MOSFET can be decided by just looking at this graph. So, just see here, this particular region has a name and this region has another name. So the names are like this, right? On the left hand side, this region is called as ohmic region, OHMIC, and this region is called as saturation, right? Two regions. Now for ohmic region, the condition is that the drain to source voltage VDS, right, should be lesser than the gate to source voltage, that is VGS, sorry, this is VGS minus the threshold voltage VTH. Threshold is something like, right, that gate voltage below which there is no conduction, right? Because you recall, until and unless your gate voltage reaches a certain value, there is no channel, right? No conduction. So that voltage is called as VTH, right? Threshold voltage. And this region, the saturation region, can be obtained if you perform this. You make the VDS voltage greater than or equal to the VGS minus V threshold. Okay, so we have the regions of operations are coming into picture because of the following reasons. All right. So what happens is, in this portion, I'm going to write what is happening over here first. Okay. So in this region, the following things are going to happen right here. So this particular region has a slope, right, proportional to the VGS minus VTH. If this gap is increasing, slope is increasing. You can see it's going up. Okay. Now, so in this region, so you see that over here, the curve actually bends, right? Moves towards a constant value. Previously, this was something like it was continuously increasing, but in this region, I can see it actually bends towards becoming a constant, correct? That is because the the channel resistance increases. Channel resistance increases at this point. Okay, then I'm going to write the last point, that is at exactly at this point, right? The point where the saturation region enters. Okay, the curve enters saturation region, in the sense, right, here current becomes a constant because, right, VGS has no effect on the channel, right? Initially, when you increase the VGS, there is increase in the channel width. But as the VDS is, if you increase the VDS further, right? I'm not touching the VGS, not the gate voltage. Gate voltage is sufficiently large, but I increase the drain to source voltage. VD is there, right? If we keep on increasing this beyond this limit, VGS minus VTH, then the VG has no effect on the channel at all, which means the current becomes a constant. Yes, so that's why VG has no effect on the channel, and hence the current becomes constant. So there is a specific condition here. This is what is going to come in the next classes. So this particular condition is called as pinch off, Pinch, pinch off. So we say that pinch off takes place because of saturation and VGS has no effect on the channel. So overall, this is the plot of IDS versus VDS of a N MOSFET, right? So these are the different things we have that happens over there. Now we need to investigate why. Okay, why this all these things will happen, we are going to see that in detail with the equations that's going to come up in the next class.